The next step in this C-bridge procedure would basically to go from the point clouds obtained during a non-contact survey and synthesize geometric models from the point cloud. Effectively, what we're talking about is basically what you see here in the picture, where there's an input point cloud and the output are these geometric solid models of the bridge with annotations or semantic markings that indicate what the different components are of this bridge. Right? And our objective was basically to show that this pipeline is actually achievable. Why do we want to do this? Earlier on, there was this discussion about bridge management systems, and our goal is basically to create an effective bridge management system. If we look at the thing, all around the outside are basically things that the inspectors do, the data they collect, the activities they do, or maybe the contractors who do maintenance. But central to that is basically this, what we call this BMS system, which is going to take all of the outputs generated by these activities and try to fuse them all together in order to create some kind of useful IT infrastructure. Central to that then is going to be the processing that is going to organize the data, to encapsulate it, and to create basically a nice software back end that will support the GUI visual front end, which will facilitate maintenance and inspection, things like that. If we consider the C-bridge process, a particular application, which is damage mapping, we have these raw point clouds, and at the bottom what we would like to be able to take pictures of damage or annotations of damage and tag the different bridge components with them. Well, when we have a point cloud, this big messy point cloud, we can't really do much with it. What we want to do is be able to synthesize these geometric models with taggable surface, texture that can be mapped onto it, things like that. So the key enabler that's gonna make that happen is effectively this 3D reconstruction that we're talking about, or the geometric modeling. Now, what we're going to consider is, what is the scope? What do we wish to accomplish in terms of a point cloud to solid model, or point cloud to what we call IFC? Well, first of all, we're assuming that no pre-existing model exists and that we need to synthesize one. Second, because it's actually quite difficult to do this with some, random scan, regular scan, what we need some high-level information from the user that will facilitate the automated processing. And then we're also limiting ourselves to specific bridge categories, in this case, girder bridges and slab bridges that are relatively straight, don't have significant curve like you would see on a highway entrance ramp, for example, and consist of a few spans, nothing too long or too complicated. As input, again, we expect a point cloud, but we also expect that it has some minimal viable density, which we've defined to be 1 point per centimeter. On the left, the bottom left, you see ones that have sufficient density, and on the right you have a partial point cloud where there's insufficient density. And you can see the vertical or the diagonal striping are basically individual laser scans, and the big gaps between them are missed laser scans. And if we have that level of lost information, there's not much that we can do. And again, we expect there to be some user guidance. Our goal is to minimize it. Ideally, we could be somewhere under an hour for the bridges categories that we're looking at. The output is going to be an industry foundation class formatted file, model file. And what the IFC formatted model files have is basically, you can think of it as a 3D CAD model of the actual bridge with metadata or tags attached to these models. What I show you here is the output we expect is around level of development around 200. You can see that the 100 level is just this aligned bounding box. Can we say basically says there is a component here, and this is its rough shape. LOD 200 starts to capture a little bit more of it. So if there's a girder, it will capture sort of the contours of the girder. If there's diaphragms, it will capture roughly the diaphragms, things like that. the abutment, the shape of the abutments and the piers. In addition to that, the IFC, the great thing about the IFC is that as an extensible format, it allows that also in its metadata we can tag the objects. So we would expect the output to not only be all of the components, but that they be tagged with their actual function, which would be column, girder, slab, abutment, etc. Given that we want to go from point clouds to this bridge model, the next question is, how do we do that? What is the procedure by which we're actually going to achieve this? And there are effectively two main categories of methods for doing this. One is it's called the top-down processing. And that one you can think of it as like, let's say you need to take apart your IKEA furniture. There's a certain procedure for taking it apart that makes sense relative to how it was screwed together. Same thing goes with the bridge. It's been designed in a certain way, and it's possible to sort of analyze the geometry of the bridge of this point cloud in order to recover what are the different assemblies, break them further down into clusters, and then ultimately components, sort of deconstructing the bridge bit by bit. The opposite is bottom-up processing. The analogy here is sort of like a puzzle, right? You have all of these little puzzle pieces and you need to create the puzzle from all of the pieces. And usually what you do is you put them together sort of based on color or based on different scene types. So these are like creating the surfaces of the bridge. We're trying to take all these individual points and attach them to different surfaces, sort of contiguous segments. Then once we have all these contiguous segments, we can say, oh, these ones are connected, they really belong to a component. Then we can build the component and then say, well, what component should be connected and how, if at all, and that gives us the assemblies and then ultimately the model. Bottom-up processing, it can actually be quite costly. If you think of a puzzle, if there's only 25 pieces, you only have to compare 25 against each piece against the other 24. But if you have 1,000 pieces, you have to compare each piece against the other 1,000, and that leads to sort of a super linear cost. Ideally, if the bridge was twice as big, it would just take twice as long, but that doesn't really hold. In the bottom-up processing, it can take 4 times longer. So naturally, really, what you want to be able to do is, because of this time cost of the bottom-up processing, often what you would prefer to do is to be able to merge the two, to have some kind of top-down partitioning to get it all down to very small puzzles, and then you use bottom-up in each of these small puzzles, and then you fuse all of the big partitions to get back together. And that's sort of, you think about it, that's sort of the methodology that we use to build a puzzle. So we want to do this, we actually want to do this with the bridge. Both approaches were pursued. One approach was pursued by the Cambridge side, the Cambridge sub-team, and the other was pursued by the Georgia Tech sub-team. In the top-down, what we have is our objective is we want to generate this solid model from the point cloud data. And the top-down then breaks down into two major tasks. One is, can we sort of detect what is the minimal component from this point cloud, the minimal components from the point cloud, and once we have that, can we actually fit or recover the geometry associated to that minimal point cloud. Looking at the first major task, what the first step is going to be the segmentation. Can we deconstruct our point cloud into different little pieces? And once we have those little pieces, can we actually make sense of them and say, these individual pieces belong to certain components of the bridge, and then we'll reconstruct the bridge by recovering the geometry and also attaching a label to that particular geometry. Top-down approaches often require some kind of knowledge or heuristic in order to create the algorithm. The nice thing about bridges is that they're often designed using architectural or engineering design criteria. We can take those design criteria, actually embed them into the sort of heuristic approaches associated with the algorithm. The way we build a bridge is the same way we would deconstruct it maybe in reverse, or the kind of knowledge we have is we know that piers support the bridge, therefore they should be under the road, right? The abutments connected back to the earth, back to earth, so we should expect them to be at the edges. Things like that are used in the top-down procedure. The visualization here on the slide shows you one way that we can embed this top-down knowledge into the procedure. Consider a bridge that's aligned along the x-axis, and look at transverse cross sections along this span direction. What you can see at the bottom is that these cross sections will vary in their geometry depending on where we are in the bridge in this cross section. We can take that knowledge and say, okay, cross sections with certain geometries must belong to certain parts of the bridge, and in particular the ones where a lot of action happen are at the piers, which they're denoted by red. If we can then identify the piers, then the geometry of these cross sections at the piers can inform us a lot about what the piers contain, what the bridge contains, and then we can then extrapolate that out and then look at also the blue ones in order to identify the remaining structure, such as the decks. And then our top-down 3D geometry process goes as follows. First, we need to pre-process it, which is the user needs to cut all the extraneous information away from the bridge, align the bridge along the x-axis, and then let the automated algorithm. The automated algorithm will create cross-sectional slices along the x, identify the pier areas. Once the pier areas are identified, then they'll then be analyzed. The analysis of the pier areas will inform us whether there are girders or not. And then finally, which will then inform how we should cut the bridge up even further. Once we have all of our partitions, in essence, each one should then be indivisible because it contains a critical component of that. And the goal would be to merge all of the individual components to create the bridge. And here's a video of it where you see in the top left the deck is slowly reconstructed from these cross-sectional slices. The piers are also reconstructed. The pier caps, are reconstructed from the cross-sectional slices, and then the piers. These then all go together to create these colorized point cloud model here, where the colors inform us about the actual component type. How well does this work, and how does it compare against sort of a traditional method? Here in this slide, what you can see are 10 different bridges that were scanned in Cambridge. In the top row, in the top of each row, you can see the original laser scan of the bridge. Then the second row will be the IFC model that we've created, which represents the actual bridge. And then below that, you can see the timing for scanning of the bridge, segmentation of the bridge, and ultimately IFC modeling once we've been able to segment the bridge. Importantly, you'll see that modeling is an order of magnitude bigger than the other two activities. The whole point of this point cloud to IFC pipeline is to basically remove that modeling time. Ideally, we would also remove some aspects of the segmentation time. So really what we're talking about is the scan time is going to be the predominant factor, and then we would maybe have an additional hour or so in the office prepping our algorithms to then do what would normally take us about 29.5 hours for these kinds of bridges. Now, to assess the output, the output of our methodology, what we need to do is actually create the ground truth. This was done by actually manually segmenting, manually labeling, and then using those labels to reconstruct coarse bounding box models of the actual bridge as depicted here. There's significant time savings. Let's consider now the other approach, bottom up with top down partitioning. Bottom up modeling is more complicated, right? If we go back to our puzzle analogy, we have to know how all of the pieces fit together, and we can maybe chunk this up, and then how the chunks then go together to ultimately create the whole thing. Here what this block diagram shows is that we've broken the bottom-up modeling into actually three different sub-processes. One is what we call surface primitive estimation. And this is, you can think of this as building a small chunk of a puzzle. Then the next part is going to be detection and classification of components. And that one is taking different chunks and saying, oh, this chunk is this part of the puzzle, and it should be connected to these other chunks. Right? Then the last part is to actually reconstitute the solid model geometry and package it into the IFC model. And that's taking our understanding of what chunks should be connected to what chunks and actually executing that connection process to generate the whole puzzle. I'm going to talk about each one in order, and also discuss to you a little bit about the timing involved and where the user comes in. So first we need user input to align the bridge, so create the bridge frame along the X, Y, and Z axes, align the bridge, as well as to clean the point cloud. What we then end up with is a nice bridge like this. No extraneous things, or very few extraneous things, and it's ready to be processed. The top-down partitioning allows us to then break it up into different levels, where you see we have the piers, we have the superstructure and the abutments, and then we have the road and upper deck components. If we continue partitioning, we can then break it down to the point where we start to build it back together very much like a puzzle. Here's an example of the pier being reconstructed from the points. On the left-hand side, we have all these points, and they're just a bunch of points. The color just is the color of the actual, that's the actual color as obtained by the laser scanner camera. On the right, we see now the orange, green, magenta, the red, all of that coloring are surfaces that have been extracted. The orange and red ones tend to be very big. As we get to the green, the blue, those are smaller and smaller. So we have a few big surfaces and very small surfaces. The next step in that procedure actually tries to then attach models to it. Oh, this is a plane. This is a corner. This is a plane. And then it says, okay, what about my neighbors? Are they planes? Are they compatible with me? Are they corners like me? And then they start to get merged, and what you end up with are still a few big surfaces, but now a few, like some medium ones. You don't have many small, many medium, you just have some now. And this procedure can take, for this bridge, was about 8 hours. For some bridges it can be up to 30 hours, 60 hours, depending on the complexity of the bridge. At this point, we have this very nice, small, sort of set of surfaces. And the idea is we need a little bit of advice from the user. Are these surfaces correct? Should some be thrown out? Should some maybe be reconsidered elsewhere? Things like that. And that user feedback takes anywhere from 5 to 35 minutes, depending on the complexity of the bridge, and depending on the complexity of the bridge. But once that procedure is done, we start to merge all of the partitions. You can see here that we have the two piers and all of their surfaces. Then we add the superstructure, which includes in this case is the diaphragm as well as the abutments. I consider the abutments part of that too. Then we have the girders. After that are the soffits, and then is the deck and the road. We've taken now, in this case, this is a 2 million point cloud, and we've reduced it now to about 280 different surfaces. The next step is to take all of these surfaces, look at their geometry, look at their placement, look at their neighbors, and say, okay, what kind of component does this surface belong to? And in addition to that, what kind of sort of object or shape, geometric shape, should be associated to that particular component? The method that we, rather than programming this, the method that we propose to use, or that we actually use, is a machine learning approach. The machine learning approach basically takes in a bunch of input-output data and tries to reverse engineer this input-output process. And what we're interested in is, we're interested in taking all of these surface primitives and outputting what the appropriate CAD label is, as well as what the appropriate component label is. And sometimes what we look at, what we're doing instead of CAD labels, sometimes what we're looking at also is maybe the mechanism by which we would reconstruct it. So is it a cuboid or is it a swept volume? Is it a cylinder? Right? Because a lot of these things can be defined as extruded surfaces, and we'd like to be able to recover the extrusion methodology. Machine learning, though, does require us to generate a bunch of training data, right? Instead, what it does is it says, if you can go and generate a bunch of input-output, a bunch of input services and output labels, then what I will do is I will try to learn an algorithm that will take you from that data to those labels. Then when it comes to implementation time, you just stick the algorithm that was automatically generated into your code base and then let it go. Our process for generating this training data and then actually training it takes about 12 hours. This is a training phase that you just do it once and then you forget, you move on. Well, you don't forget, but you use the output of that in your algorithm and then you no longer have to train it again. Unless you would like to add new bridge classes, new categories, new things like that, then you would have to retrain. In the implementation process, what you have is you have the procedure that I had outlined before, point cloud to surface primitive estimation. At that point, the surface primitive estimation is then fed to the classifier, is processed and fed to the classifier, which will output the CAD and component labels. And I drew the arrow from the top to the bottom to indicate that really the output of the training phase is an actual algorithm, right? So it's a data structure that I can then load and it will execute an algorithm for me. And the execution of this algorithm is significantly faster than the training phase. We're talking 5 to 10 minutes. But again, the number will vary depending on how many surfaces you have in your point cloud. So this 5 to 10 minutes is roughly for a point cloud that will have about 200 to 300 surface components. If you have 1,000, then that's going to take 3 times longer. It's going to scale linearly. Here's a sample output model of the CAD classification. Because this bridge had no cylinders, everything is either a cuboid or a swept polygon. Now, here's also a sample output of the bridge component classification, and you'll notice that they're color-coded based on the bridge component type, and we roughly get everything correct. At that point, our next step is to take all of these CAD labels and the component labels and say, okay, how do we rebuild the bridge from this? You should have noticed that all of the column labels were near all of the column surfaces were near other columns. The pier cap were near pier cap. The abutment were near abutment. And so we can take that and say, oh, these are connected. They're all the same type. So therefore they must be merged to create a single solid model component. That's what happens in the reconstitute solid model geometry. Once we've recovered it, we now have a parametric model that can then be put into the IFC. Here's an example of our initial processing where we had synthetic data and we looked at very simple slip bridge. We also looked at a very simple beam bridge. This is the kind of data that we not only synthesized, but we also fed to the training algorithm. But then when we implemented it in real life, rather than using that kind of synthetic data, we actually use this real data over here. You can see this is the Ackworth Bridge. I'm showing you the underneath so you can see the girders, you can see the diaphragms. Then here's the actual IFC model that gets generated. You can see we have the road, this is color coding. We have the decks, we have the abutments, we have the girders, the pier caps, and the piers themselves. In a moment, I'm going to start to show you the IFC model properties. So you can see we've labeled the deck components. Anything that's part of the parapet, we just sort of give it this other name. I'm going to then show you here the middle. We see the diaphragms, the ashtoe girder. So the important in this, we've actually broken the bridge down into 3 levels, right? The lower level, a middle level, and an upper level. Here you're looking at, I've hidden the upper level so you can see the lower level, the middle and lower level with the girders and the abutments. I'm going to hide this middle level and only leave the lower level now, which is quite boring, the pier cap and the pier. In terms of time, what we can see here is that user time for this, the bridge that I just showed you, the Ackworth bridge, is under half an hour. This includes the bridge cleaning, the pre-processing, reviewing the 282 components, and kicking out the ones that are basically garbage. Right? They're not necessary. Or telling the algorithm that it needs to take one small component and merge it with another component. One surface and merge it with another surface. On the Haifa bridge, we have roughly right now an hour of user intervention and about more than 60 hours of processing time. Look, if you look at it, the 59 of those hours were basically segmentation. It took about 2.5 days to do the segmentation. The Haifa bridge is significantly more complicated than the Ackworth bridge. It has 10 girders per span section instead of the 5, as well it has more diaphragms. And the abutment is roughly the same complexity. The deck is a little bit more complicated here for the Haifa bridge. I have yet to do the Cambridge bridges, but they should be done sometime soon. What about the accuracy? We haven't really been able to fully explore the accuracy, but what we have been able to explore is how well is the surface detection part. What this shows here is that the Ackworth bridge had 4 out of the 286 component surfaces that were identified, 4 needed to be thrown away or merged with another surface. When that was done and the model was generated, the bridge consisted of 282 solid model components, when in fact there are really 280. These extra 2 components are basically an abutment that was broken up into 3 parts instead of remaining 2 parts. If you look at the solid model, it will look totally fine. Nothing is, all the surfaces are there. However, when you go try to look at the abutment, you'll see that this one piece is really now 3 pieces. All of the components were detected. In terms of dimensions, we haven't really checked if the lengths are correct and how accurate they are, but everything looks pretty good, except the one girder was about 20% longer than all of the other girders, so we could definitely consider that to be a mistake in the dimensions. For the Haifa bridge, we haven't quite finished the processing, but in the initial processing and the user feedback strategy, 57 surfaces out of 807 needed to be either deleted or merged with a neighboring surface, which represents about a 7%. 7%. You can think of it error rate or accuracy loss. The over segmentation, we haven't figured that one out yet, but once we have the IFC model, we'll know the answer, as well as the components and dimensions. All right, let's summarize these 2 methods now. In terms of time, the top-down method was the most efficient, right? User time was roughly half an hour. Algorithm time was roughly half an hour. And then you had the output. So within about an hour, you have your output. However, the level of detail is at 100, and the output is bounding box descriptions. The only components you can get are the deck, the girder, a bounding box model of the deck, the girders, the pier cap, pier column, and pier. So we could think of it as sort of the essential visible components of the bridge minus the abutments. On the bottom-up method, we have significantly more user time. We can have up to an hour or a little bit over an hour of user time. The algorithm itself is also much longer, taking a few to many hours, a few hours to basically 2 or 3 days. However, the level of detail is at the target level for the critical components, and it's below the target level for the non-critical components such as the parapet, the soffits, and extraneous components of the deck. The output is an actual IFC model that can be browsed by level, and it has all of the components noted below. However, not all of them will be labeled. The abutment and the wing walls are simply labeled abutment. The parapet is also given some arbitrary label. What about the limitations of the method? In the top-down method, we have not achieved LOD 200. I don't know if we have IFC output. I'm going to assume we don't. And there are several missing components. Most importantly, the abutment area. In the bottom-up cloud, the bottom-up method, we have, what are some of the issues? One is if there are missing points in the cloud, then we simply cannot reconstruct that. If there's insufficient point density, then an entire surface could be missed, which may impact the ability to regenerate that component. And there's also the possibility of parametric error. The reason that one of the girders was 20% longer was because there was this set of points that appear to be phantom points. They don't really belong there. It's most likely a laser scan error or some kind of reflection. But these points lived beyond the extents of the actual girder and were considered part of the girder. Additionally, missing components are things that are small or that involve fine level features associated to the piers or the abutments or things like that. This can't really capture detail features, which would be more compatible with LOD 300. Something we could consider an issue is that not all the bridges have been processed. Since it's a more complex algorithm, it's taken longer to program, to program, and so we're not quite there yet, and the validation isn't as complete as for the top-down. However, we have actually achieved our objective, which is take this point cloud input and generate solid model estimates of the bridge as output. And not only that, but also have them semantically labeled. Right? Our top-down approach, again, achieved the LOD 100, and the bottom-up approach achieved an LOD 200 plus, which means that we've effectively created this algorithm that now allows us to do the remaining parts of our sea bridge pipeline. And importantly, there are significant time savings involved with generating this model. And in fact, the important part is that it's an order of magnitude less than the manual procedure, so that makes it actually that makes it sort of manpower effective. And not only that, the amount of user involvement is still less than the amount of time required to laser scan it. So if we think about what is the added amount of effort needed to be able to admit the remaining parts of the sea bridge pipeline, it's actually less than the amount of time required to laser scan it. And this model would basically persist from year to year to year. So it's a one-time thing, which is quite cheap when you consider how long a bridge lasts and how much inspection time is associated to it.